We come to a more general matrix, like it's not even normal. So A has the eigenvectors phi. It doesn't have to have a label, but say you have eigenvalue lambda, and then we can consider the A decker also. But if A decker A is not normal, A decker is not commute with A, so you don't necessarily have the same eigenvector. Where you can still show that the eigenvalues can be complex conjugate to each other, but eigenvector generally not the same. So A decker now operate on a different eigenvector psi, and we can show that this the eigenvalue is lambda star psi, and which we can show by a very simple the analysis, just taking the scalar product. Say the first equation, you have A operate on psi or on phi. So A phi, and take the scalar product with psi, right? And then using the first equation, the the right hand side has a lambda, so you pull out the lambda. So lambda times the scalar product between psi and phi, right? Then we can use the definition of adjoint operator and change that to equals A that operate on psi on the left. And now you can use the second equation, but now generally we can just assuming the eigenvector now is Cassini and found the relation with Cassini with lambda. Now you can pull out Cassini out, but when you pull out, you have a complex conjugate because it's on the left slot. And now these two equations show that so Cassini complex conjugate is equals to lambda, or the other way around, Cassini is equals to lambda complex conjugate. So that is still valid for even for non normal matrices. The eigenvectors are not the same, but they can still have the same eigenvalues for some eigenvectors. So that's the more general case, and there's even one more general case. It's even more general case is that the matrix may not have all the numbers of eigenvectors, eigenvalues, eigenvectors. Say you have a 2 by 2 matrix in your textbook. This matrix, you go through the process of find eigenvalue, eigenvector, and you can show that it only have one eigenvectors, and that is pretty straightforward. And that's called defective matrix.